Oh, you're welcome. Okay, so organic chemistry. So we are gonna start with the introduction to organic chemistry. So, first, let's define the term organic chemistry. Organic chemistry is the chemistry of carbon compounds, right? And the major element in organic chemistry is the carbon. Okay. Now, carbon is actually the central element in organic chemistry, and in this particular course, we'll study the chemistry of carbon compound. Now, there's an exception. Okay, there are some inorganic. There's some inorganic carbon compound. We don't study in organic chemistry. Okay, for example, the triazocarbonates. Okay, triazocarbonates are they are not regarded as organic compound. Even the oxides of carbon, for example, carbon 2 oxide and carbon 4 oxide, okay, are not regarded as organic compound. Even the carbides, okay, metallic carbides, they are not regarded as organic compound. So except all this compound that I listed, every other compound, right, is referred to as organic compound, and we're going to study them in organic chemistry. Okay, so now the question is, where do we get this organic compound? Now, it was actually it was noted and it was inferred that anything known as organic compound, okay, are actually compounds which are found in nature. They are found in nature and they are not, okay, they are not synthetic. Not synthetic. That simply means that you cannot manufacture them in the laboratory. Okay, so anytime the word organic compound is being mentioned, okay, you're looking at a natural occurring compound that is not man-made, right? That cannot be manufactured in the laboratory. But the idea that all organic compound cannot be manufactured in the laboratory is not relevant anymore, because most of the organic compound now can be manufactured in the laboratory. For example, urea, okay, can be manufactured in the laboratory. So that way, we cannot just define organic compounds to be the compounds that are found in nature that are not synthetic. Okay, so as I said, the central element of organic compound is carbon. Now, we have varieties of organic compound. Some can be manufactured in the laboratory, some are found in nature. So there are over 5,000 discovered organic compounds. Now, these 5,000 discovered organic compounds, okay, of course, I also have the central element in that compound is carbon. All right, they are not all that is there in nature. Okay, more and more of this compound are being discovered every day. Okay, so we simply mean that you have innumerable number of compound that you can actually discover from nature, and all these compound have the central element to be carbon. Now the question is, why is it that carbon, right? Carbon actually forms innumerable or varieties of compound. Okay, Now, the reason why carbon actually forms the varieties of compound is the ability of carbon to form bond easily with other elements. Ability of carbon to form bond easily with both the metals and non-metals. Okay, you know very well that carbon is a metalloid. It's a metalloid. Okay, it's found in between the metals and non-metals. So carbon can form bond easily. Okay, easily with metals and non-metals. Okay. All right. So that's number one reason. Number two reason is the ability of carbon to catenate, or catenation is actually a process, okay, that involves the formation of straight chain, branch chain, or even chain in a ring. So the ability to form chains, ability of carbon to form different types of chains of compound. Okay, now let me give you a typical example. Let's look at this particular carbon compound. 4 carbon, right? And this is a straight chain carbon compound. Straight chain. Now, if this straight chain, please, pardon me, let me clean up. All right, now this is a straight chain. This straight chain can actually form branch chain to give a different compound entirely. Okay, from this straight chain, I can actually create a branch chain organic compound. Now look at how that will happen. All right, I can take, okay, any one of this. I can take any one of this group and put it as a branch chain. Okay, so I'm bringing the dot here. So this is actually a branch chain. So now the same number of carbon atom, all right, and hydrogen, but here I'm having 2 different compounds. Okay, what I call this butane. This, on the other hand, still having the same number of carbon atom and hydrogen, is called 2-methyl propane. Okay, now the same number of hydrogen and the carbon atom can still rearrange, okay, and form what is known as ring chain. Okay, so therefore they can join end to end to form a ring chain. Then I can now place the hydrogen. Let me just write it in a condensed form. H2 is the 2 atoms of hydrogen, H2. Okay, now this is another compound entirely from another family, and it is called cyclobutane. So you now discover that just one compound, I'm able to actually form 2 other compounds from different family entirely. So this ability of carbon to undergo catenation is one of the reasons okay, while we have varieties of carbon compound. Okay, I hope that is well understood. All right, so let's proceed. Okay, so pardon me, let me clean up. So now we are going to be looking at the terms that is used in describing organic compound. Okay, there are terms that are used in describing organic compound. Those are the terms we are going to be focusing here in this video. Okay, so in describing organic compound, there are important terms that we need to actually. So let's look at the basic concept. Okay, so I'm going to actually list them out. I will list them out. Now, number one, we are gonna have. We'll talk about the electronic configuration of carbon. The electronic configuration, and of course, the bonding of carbon. Bond formation of carbon. Number two, we are going to talk about a phenomenon known as homologous series. Number three, we are going to discuss the meaning of alkyl group, alkyl family. Number four, we'll talk about functional group. Number five, we will discuss formula of organic compound. Formula of organic compound. Then after which we will now talk about the IUPAC nomenclature. Okay. All right. So we're going to begin. Now, the very first concept that we need to discuss is the electronic configuration of carbon and bond formation. Okay. Now, carbon, as we already know, has six electrons. So if we should write the electronic configuration of carbon, okay, using the energy level, the inner shell will have two electrons, while the outer shell has 4 electrons. Okay, so that means carbon has 4 valence electron. All right, now because of this 4 valence electron, carbon is said can form a total of 4 bonds, because each of these valence electron can be used to form covalent bonds. So carbon only forms bonds, known as covalent bonding. And of course, you know that covalent bonding is a bonding that that involves the sharing of electron. So each of these 4 electrons, carbon will share with other neighboring atoms, or even with another carbon to form a 4 covalent bond. Okay. Now this bond is directed tetrahedrally around carbon. For example, in methane, there's going to be a bond between carbon and hydrogen. A bond. This is a tetrahedral structure. Okay, 4 hydrogen atom bonded with 1 central carbon. All right. Now, of course, this is actually, if you look at this, you actually think that the angle between each bond is 90 degrees. No, this is just for simplicity. All right. The angle between each bond is 109. Okay, if I'm not mistaken, 106.9. Okay, so that's the bonding. So which simply means that by simplicity we actually draw this. Okay, but if you really want to draw how bond, okay, you want to draw the bond formation of carbon. All right, you discover that it's not as simple as what you see here, but the bond is in a 3D form. Of course, you know what 3D means. It simply means that some of these bonds are actually behind, some bonds are coming forward, right? So this is just for simplicity. Now, so carbon forms a total of 4 bonds around its atom. Okay, so now sometimes carbon can form bond between another neighboring carbon. When that bond is a single bond, okay, carbon can form single bond with another carbon. Carbon can also form double bond with another carbon. Okay, carbon can form triple bond with another carbon. Okay, now this is actually possible due to the phenomenon known as orbital hybridization. Now I will not discuss this in detail. All right, so there's a particular orbital hybridization of carbon that will actually lead to carbon-carbon single bond. Okay, there's going to be orbital hybridization of carbon that will lead to carbon-carbon double bond. There's an orbital hybridization of carbon that leads to carbon-carbon triple bond. Okay, so let's look at that orbital hybridization. Of course, you know what is orbital. Okay, the hybridization of orbital for carbon-carbon single bond is hybridization of 1x and the 3p orbital. Okay, just one of the x and of course 3p orbital. So that's why we call it sp3 hybrid orbital. When the x, okay, 1x, of course you know that x is the lower orbital, okay, of lower energy, p is the higher orbital of higher energy. So when 3 of the p orbital comes to overlap with 1x orbital, you have what is called sp3 hybrid orbital. Okay, so now from this, now you can simply say that the ratio is 1:3. The ratio of x to p 1:3. Okay, so if you put this in percentage, you will have this sp3 hybrid orbital will only give 25% of x character, while the rest 75% for p character. Okay, so now let's talk about the one of double bond. The one of double bond, okay, the hybrid orbital is sp2. That is 1x and 2 of the p orbitals we actually overlap to form a hybrid orbital. Okay, so from here now you can see the ratio is 1:2. Okay, so invariably, okay, from here the B character is always is double, 2 times the X character. Okay, P character is 2 times the S character. So if you want to actually convert that to percentage, that's going to be 2 all over 3 times 100. But let's not go into that. Okay, then finally this is SP character. So both the ratio of X and P is 1:1. Okay, for carbon-carbon triple bond. So please take note of this. So we have here for single bond we have sp3 hybrid orbital, double bond we have sp2 hybrid orbital, then triple bond we have sp hybrid orbital. Okay, so I hope that is well understood. Okay, so we'll look at the next concept. Okay, so we'll talk about the homologous series. Homologous series. Now, since we know that there are varieties, okay, thousands of carbon compounds have been discovered. Now, it is very ideal for this compound to be placed in families, okay, so that compounds that have similar characteristics will belong to one family. So, homologous series is defined as the family of organic compound. So, it's a series. It's in form of a series. So, a series that actually lists of a particular family of organic compound. Okay, so homologous is a family for organic compound that follows a basic, okay, that follows basic structural patterns. It follows, okay, a regular structural pattern in which each successive member differ by the molecular formula. CH2. Okay, so here, so homologous series is actually describing the family of organic compound, right? And that family, the members are arranged in a regular structural pattern. That means one has a structure that differs from the other, but it's in a regular form. Okay, and each successive member differ by CH2. That means the member that is lower, the one that is actually higher than the other, will actually differ, okay, by the CH2. The difference is just CH2 molecular formula. Now, for me to illustrate this, okay, let's look at example of one family um, in homologous series. Okay, let's look at the alkane family. Okay, so alkane family, I'm going to arrange a series, so it's going to be a list of all the members in alkane. All right, the very first member is called methane, and you know very well that the member will have just one carbon atom, that's CH3. Okay, now the second member, as I go down, then the number of carbon atoms will increase because each level will actually differ by CH2. That simply means that if I want to write the second member, I'll have to add C to the previous and add H2 to the previous. So the next member is called ethane. So I add C to it to give me C2, then I add H2 to this H3. Please, this is CH4. Okay? Methane is CH4. Please pardon me. Okay? Then I add, if I add 1 to this, I have C2. If I add 2 to this, I'm gonna have, if I add 2 to 4, I'm gonna have H6. Okay? So the difference between this and this is still CH2. The same thing happens to the third member, okay, which of course is propane. Propane is the third member. Add 1 to the C2, I'm having C3. Add 2 to the H6, I have H8. Okay, proceed. Number 4 is butane. C4, H10. Have pentane. C5, H12. Have hexane. C6, H14. We have heptane, that's number 7. C7, H16. Then we'll have octane, number 8, C8, H18. We have nonane, number 9, C9, H20. Then we have decane. I'll stop at number 10. Number 10, decane, C10, H22. So this is the homologous series for the alkane family. Okay, so in the next video we are going to look at the major characteristics of a homologous series. Okay, all right, see you in the next video. Thank you very much.